Which move faster on a merry-go-round, a horse near the outside rail or one near the inside rail? Why don't the riders out the rotating carnival in a figure 9.1 is raised? If you swing a tin can at the end of a string in a circle over your head and the string breaks, does the can fly directly outward or does it continue its motion without changing its direction? Why do astronauts orbiting space shuttle float in a weightless condition, whereas astronauts orbiting in some future rotating space station will experience normal Earth gravity? These questions indicate the flavor of this chapter. We begin by discussing the difference between rotation and revolution.
Rotation and revolution. Both the rotating platform of the carnival ride shown in figure 9.1 and on an skater doing a periodic turns around an axis. An axis is a straight line around which rotation takes place. When an object turns about an internal axis, that is, an axis located within the body of the object, the motion is called rotation or speed. Both the carnival ride and the skater rotate. When an object turns about an external axis, the motion is called revolution. Although the platform of the carnival ride rotates, the riders along the platform outer edge revolve about its axis. Earth undergoes both types of rotational motion. It revolves around the sun once every 365 days, and it rotates an axis passing through its geographical poles once every 24 hours.
To better understand what was explained, here is a video from OpenStax.
For decades, the Winter Olympic Games has drawn people from across the world to marvel at breathtaking athletics on the snow and ice. One of the most popular events is figure skating. Athletes meld acrobatics, dance, and physics into mesmerizing performances. It is the sheer precision that separates the skilled athlete from the novice. Through years of tireless training, skaters must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
(9.2) Rational speed. We began this chapter by asking which moves faster on merry-go-round, a horse near the outside rail or near the inside rail. Similarly, which part of turntable moves faster on the pre-CD record player shown in figure 9.2, which part of the record moves faster under the stylus, the groove at the outer part of the record or the groove near the center. If you ask people these questions, you will probably get more than one answer, because some people will think about linear speed while others will linear speed, which we simply call the speed in chapter 2, is the distance moved per unit of time. A point on the outer edge of a merry-go-round or turntable moves a greater distance in one complete rotation than a point near the center. The linear speed is greater on the outer edge of a rationing object than it's closer to the axis. The speed of something moving along a circular path can be called
a central force, a force of some kind of required to maintain circular motion. Any force that causes an object to follow a circular path is called of centripetal force, means central seeking or toward center. For that holds the occupant safely in the rotating carnival ride. It is a center-directed force. Without the motion of the occupied would be along a straight line they could not revolve. Potential force, the main role in the operation of a centrifuge. A familiar example is the spinning tube in an automatic washing machine. The tube rotates at high speed during its spin cycle. The tube inner wall exerts a centrifugal force on wet clothes which force into a circular path. The tube exerts great force or the clothes, but not the tube. The same force of the water in the clothes. The water escapes through the holes. It is important to note that a force acts to the clothes, not the water. It is not as the water escapes. The water escapes because it tends to move in inertia in a straight line path, unless act by the centrifugal force.
I am going to discuss about centrifugal forces and centripetal force. But before that, I am going to introduce myself. I'm Daphne Morinti Altida, grade 12 Spirulina, group 1. Second situation. Now, suppose there is a ladybug inside a whirling can. The can presses against the bug's feet and provides the centripetal force that holds it in a circular path. The ladybug in the torrent presses against the floor of the can. Neglecting gravity, the only force exerted on the ladybug is the force of the can on its feet. From our outside stationary frame of reference, we see there is no centrifugal force exerted on the ladybug, just as there is no centrifugal force exerted on the person who pitches against the car door. The centrifugal force effect is attributed not to any real force, but in inertia, the tendency of the moving body to follow a straight line path. The can provides the centripetal force necessary to hold the ladybug in a circular path. Today, I hope you learned something new. Thank you. This is the total if you divide that 1,600 over 8. So, we need 200 and centripetal force. Yeah. And for the mass, it is 100 kilogram from right here. So, times the speed, let make us squared. So, 100 times 4 squared divided by 8. We solve the mass times the speed first. So it answered 1,600 divide over 8. And for the mass, it is 100 kilogram from right here. So times the speed, let make us squared. So 100 times 4 squared divided by 8. We solve the mass times the speed first. So it answered 1,600 divide over 8. And example problem. A motorbike and rider of total mass 100 kg travel round a roundabout of radius 8 meter at a speed of 4 meter per second. And the question is, what is the centripetal need to do this? Both centrifugal and centripetal force have the same formula. And this is the formula. F equals m plus v squared divided by r. F is for force and m is for mass. V is for speed and r is for the radius curvature of the moving object. To answer the problem, first, we must copy the given or find the given. The given mass is from right here 100 kilogram and the tangential speed is 4 meter per second. And the radius is 8 meter. And for the second, we must write the formula. And the formula is force equals mass speed squared over radius. You got it.
Centrifugal force in a rotating reference frame. Our view of nature depends on the frame of reference from which we view it. For instance, when sitting on a fast-moving train, we have no speed at all relative to the train, but we have an appreciable speed relative to the reference frame of the stationary ground outside. From one frame of reference, we have speed. From another, we have none. Likewise with force. Recall the ladybug inside a whirling can. From a stationary frame of reference outside the whirling can, we see there is no centrifugal force acting on the ladybug inside the whirling can. However, we do see centrifugal force acting on the can, producing circular motion. Thus, from an outside stationary frame of reference, the only force acting on the ladybug is the centrifugal force exerted by the bottom of the can on the ladybug's feet. In a rotating reference frame, the central figure force refers to the apparent force experienced by an object due to its motion in the rotation frame. This force is often called the centrifugal force and acts outward from the axis of rotation. It's a result of inertia of the object trying to keep it moving in a straight line within the rotating frame. This force is fictitious, as it does not arise from any physical insertion, but is a consequence of observing motion from a rotating perspective. For example, imagine you're inside a car making a sharp turn to the right. In the rotating reference frame inside the car, you feel pushed towards the left side. This sensation is due to the centrifugal force acting outward from the center of rotation, the turning point. Even though there's no actual force pushing you to the left, your body tends to continue moving in a straight line, creating this apparent force in the rotating reference frame.
Today, we live on the outer surface of our spherical planet, held here by gravity. Earth has been the cradle of humankind, but we will not stay in this cradle forever. We are on our way to becoming a space-faring people. In the years ahead, many people will likely live in the huge, lazily rotating space stations, where centrifugal force simulates gravity. The simulated gravity will be provided so that people can function normally. Occupants in today's space shuttles feel weightless because they lack a support force. They're not pressed against a supporting floor by gravity, nor did they experience a centrifugal force due to spinning. But future space travelers need not to be subjected to the weightlessness. Their space habitats will probably spin like the ladybug's spinning bicycle wheel, effectively supplying a support force and nicely simulating gravity. To better elaborate on how simulated gravity works, or artificial gravity, here's a video.
Hey, I'm Mike from Small Stars. Let's talk about how artificial gravity works. But it would be fun to first start with real gravity, of course, which technically isn't even a force, so it's complicated. You can think of it as matter filling up volume in a space that the universe really wanted to be empty. The mere presence of matter disturbs space, and therefore time, which is what causes objects to attract and accelerate towards each other. In contrast, artificial gravity is fairly simple because it's just an imitation of real gravity. On a spinning space station, the spin starts off with thrusters giving the edge a push. If a section of the edge broke off, it would travel away from the station, right? The tension that keeps everything together is continuously pulling the edges of the station inwards, which is what causes centripetal acceleration. If the radius of the spin is large enough, you wouldn't notice the spin at all, but you would feel the floor resisting and constantly pushing up on your feet, just like the floor underneath you is doing right now.